Okay, my friends, get ready. This is going to be a discussion about Neil deGrasse Tyson. His remarks about Terrance Howard and his research. Now, I want to be involved in this research too. Here's his statements about what it takes to be an expert. Now, I could do this disrespectfully or I could do this respectfully. I'm going to try to be respectful. I have not found that from the other side since I started my research deeply for 15 years. And it takes a long time to be sure of what you're saying. And it takes a lot of tests. And it takes a lot of experiments, which I have done all of those things. And I have found out that I am correct, I believe, unless somebody can prove me wrong. That's what science is about. Just as he'll talk about it in a minute. Okay, again, he's talking about something called the Dunning-Kruger effect, which means you learn a little bit about something and then you think you're a genius. And then everything you say, you just spout it out like you're a genius. Now, he's saying he's taken many years to become expert at what he's talking about. And here's what he's saying. An expert requires years and years of study. Now, I'm going to let him speak. And again, this is Fair Use Act. I'm just commenting because I'm going to tell you, he's going to say that everything that Terrance Howard based his research on was wrong. So everything he's going to say is going to be wrong. I say everything he's basing his research on is wrong about subatomic particles. So therefore, the rest of his research is wrong. That's my statement, and I'm not doing that disrespectfully. I'm just saying I want him to show just exactly the way he's talking about addressing peer review. I want him to peer review me. Here goes.
Actually, looking through journals where new ideas are published and contested, that's what we have learned is the most effective means of establishing that which is objectively true, or determining that which is objectively false. Both of those work hand in hand to move the needle on our understanding of the universe. I'm going to read you just my opening line here. It's titled 1 times 1 equals 2.
All right, this is where it just gets silly. They're going to get into all kinds of crazy nonsense of equations. 1 times 1 is 1. 1 of anything is 1 of that thing. I don't care how you do your math. They're going to tree on all kind of nonsense. And this is what happens. All right, I'm going to try to be respectful. But this is what happens in academia. It's just nothing more than a bunch of fluffy nonsense to bring up some convoluted idea that makes you jump to the top of the pile and say, oh, 1 times 1 can't be 2. Well, no, it can't be. But this doesn't make him a genius for pointing that out. Now, I'm going to show you what I can present and what I have been denied to present. Okay, what's the smallest particle that they know of in physics? They're talking about the proton. No, light is a particle, and light is much smaller than a proton. Okay, so Neil deGrasse Tyson. I'm just going to go by first names. Neil, I'm going to call you Neil. You can call me Roger. Okay, how's that? All right, so anyway, here's what Neil has to say. He's, as far as I know, he's sticking with the standard model. Now, if he isn't, I'd like to know why. Now, this is the research that we did. These pictures are literally pictures of light experiments that Rod Warren and I did years ago. And this, my friends, is from Fermilab, all right? And this is ours. We found the exact same particles that they found in Fermilab. But here's the problem. Fermilab hits big particles together like this, protons and neutrons. All right, and they smash them together and they get all this debris. And they call it a particle zoo. Yes, because they're really hitting on 2 of these, which each one of these has almost 2,000 particles. It's this big. This is what a proton really is. All right, and a neutron is just a proton with 1 extra electron particle attached to it, 1 extra gluon, which I'll show you all this very carefully in a minute. But when they hit together, chunks go flying. But guess where the dark matter is in the universe? All the light that's in here right now contains dark matter. All the stuff right in the air is all full of dark matter. Well, where is it? All we know about is protons. The smallest particle that exists, they say, is a proton. Somewhere here, hold on. Okay, as I said, I'm going to be respectful, and Neil seems to feel that peer review is required when there's evidence presented. Now, this is from Fermilab. Now, this goes way back to 2013, and these are the particles that Fermilab found, the smallest particles that exist, and that's a fixed particle, never changes. That one gets big and small and has virtually no weight. And this was from Don Lincoln at Fermilab, and he asked if you have any questions and so forth. And I did contact him. Now, he also posted this one, same sort of time frame, looking for Dirac neutrinos or Majorna neutrinos, and what is the difference between those. And he also posted this one at the same time, saying that the universe is not empty. Empty space isn't empty. The universe is filled with particles. They wink on and off like bubbles on a root beer. They blink on and off as they are being excited and unexcited. Now, I'm going to show you our research that shows he's correct about all those things. All right, let's just start off with a couple of claims that I will make versus the claims that are made by the standard model. They say that quarks and leptons are considered the smallest known building blocks of nature. Well, but you have to smash these particles into a billion pieces before you can see these. They're subatomic particles. That means they're smaller. They're smaller than atoms. Subatom. They're the fundamental components of hadrons. They got so many names now, it's unbelievable. They're indivisible. You can't break them down anymore, they say, and cannot be broken down into any smaller components. Quarks have fractional electric charges, but when they combine in groups of 3 to 4 baryons or in pairs to form mesons, oh, this just gets nonsense. Let me show you what the particles are made of. Let me show you what a proton is made of. It's not this. It's not this big gigantic thing that you can smash into get quarks and things. It's made of all these dipole electrons. And at 1823, approximately, they lock in and become stable. And a hydrogen is made of about 1825 or so because it has a stable core, and then more want to get in. Because the black center, and I'll show you that in a second, whereas the dark matters in every single atom there is the dark matter is in the core. That's why it has weight. That's why everything weighs what it weighs, because the dark matter goes to the center. We never see the dark matter because you only can see the outside. And the outside never shows the dark. But this would be a hydrogen. And it would say, all right, I've got just exactly the number of particles for me to be stable. That's called stability. Now, one more says, boy, I'd love to come in there. I says, no, you can't come in. He said, well, what do you want me to do? I said, stay right out there. You stay that far away, and we won't bother you. And so that's a hydrogen. It's got the core with like one little extra one. It wants to get in, but it can't. All right, but sometimes they will get pushed in there. Then it's called an isotope. It means it has more of these particles than it should have. Sometimes it has less. And then it's like a negative isotope, and sometimes it's a positive isotope. It has more electrons than it should have. Now, where's the dark matter? I don't see it. Do you? Well, guess what? I do. There it is right there. There it is in the center. In the subatomic realm, you can separate the black from the white. You can't do that once you get to atoms. Once you get to atoms, you break an atom like this here. All right, you see these? These are bar magnets. All right, I can't push this. These two won't go together because they're going to push each other apart. But if I turn them around like that, they will attract to each other. Now, if I broke this apart, I'd have 2 bar magnets. I'd have a bar magnet here and a bar magnet there. I break it again, it's 2 more bar magnets. But once I get to the nucleus, and I started breaking up the atomic core, then the blacks separate from the white very easily, and I'll show you that actually happening. So the quarks and leptons, I say that's not true. I say the only thing that exists is these dipole electrons, and they form in masses. I call it dipole electron flood theory. And that's the only thing that exists, and light, my friends, from 1970, energy, the transfer of energy is from light to atomic vapor. Just the same way you have mist and fog, and when it condenses, it turns into water. Well, light, when it condenses, it turns from atomic vapor into matter. There's nothing that isn't made out of light. It's the building block of matter. You see, they say that the leptons and quarks are the building blocks of nature. I say light is the building block of nature. All right, I got pulled away for a minute here, but I think I showed you this, which is the Fermilab particles. They find these at CERN and Fermilab and all the Lawrence Livermore. And I've corresponded with all these people. And I actually went to, I didn't go there, but I took particle physics at the University of Geneva. And I showed them all this stuff. And I think it impressed them, first of all. Secondly, I think they might have made some changes to CERN to use the CMOS, because when I first showed them this, they said, no, you're crazy, you can't see these particles, it destroys the CMOS. I said, well, we're using light, you're using protons, so we're using particles this big, and they don't damage it. They're made to deal with these particles. That's exactly what CMOS is made for. But once you hit something like this, boom, and they do, in their colliders, because they're dealing with these big gigantic things. They destroyed the CMOS, and they upgraded. They went and put all new sensors in there to be able to see using CMOS. See this? This is at CERN, and this is about development of high voltage CMOS sensors. CMOS, the complementary metal oxide semiconductors, silicates, whatever you want to call it. And the reason is for radiation tolerance. Exactly. They said you can't use it. I said, yes, you can if you're using light. Well, they still want to work with the protons. So they had to figure out some way of making it tolerant. And so they must have put some kind of filters in there to take out all the big particles before it hit the last little particles. But then they're interfering with what they're actually seeing. All right, we're actually seeing what we're actually seeing. We don't have to put any filters and harden things, because that's what they're doing. They're putting in, I don't know how they're doing it, but they have to stop the heavy-duty radiation from hitting the CMOS. Otherwise, they're going to destroy it. They're right, because they're using too big of a particles. They want to find the smallest particles that exist. Why don't you start with the smallest particles, which is light? Let me show you. All right, I think I know I showed you this, but let me just explain one other thing here. Here's what Don Lincoln is saying. The point-like particle will not change in size. The black one never changes in size. It's the same size forever. They're all the same. Black, white, the green, the red, the blue, same size. Now, but the point-like particle, this one here, will not change in size, but the more closely you look at it, the stronger the field surrounding it becomes. That's because you're putting energy into it, so the field is getting pushed out. That's why they had to go to CMOS. CMOS accepts the particles. They want to go in and look at them with some kind of energy, and that's what's called the observer effect. They say every time we look at them, they change. Well, that's because you're adding energy into it. It's not because you're looking at it. We're looking at it with the CMOS, but the CMOS doesn't do anything except take the particles that are coming at it. And that's what it's designed for. But you can't use these big, gigantic particles when they're big. These you could use. These are what turns our CMOS on. Now, he said at the end here, all right, in summary, the extended particles, the black one, has a fixed size. It's fixed forever. It has a fuzzy edge, but the point-like particles are a mathematical abstraction, zero size. I'm not sure about that. I think they're more like soap bubbles. Now, even zero-size particles have an extended field due to the effect of the field surrounding them. So something's surrounding them. And I think it's almost like a soap bubble. It has almost no weight whatsoever ever to it. But there's got to be some kind of fabric there, I would think. I can't see nothing causing this kind of energy. And I'll show you the energy we're talking about. All right, so don't forget, that's his particles, Don Lincoln's. Never changes size. This one gets big and small. And here it is right here. This one's getting bigger, and that one's getting smaller. And why would that happen? This one is going through the air this way and concussing with all the particles in front of it. I don't think you'll be able to see that. Maybe. You see those little particles? They're glowing and making the one trying to push through it glow. And in the same time, you've got your black and white particles there. All right, these are the Dirac neutrinos. There's a black and a white and a black and a white. That's it. And it has a glowy edge around it. All right, which it does. Exactly correct. And it never changes size. Exactly correct. This one gets big and small. Exactly correct. And it is getting bigger because it's pushing through other fields. It's field effects that cause these things. Now, we were able to put this through a venturi. Here, you see the particle accelerating right out of its wave. And there's the particle until it actually breaks right here. The white separates from the black, and then it comes back together here. Right in here is electron showers. And that's exactly what they say. This is from CERN or Fermilab, one or the other. Muon neutrinos and electron neutrinos, which is the black and the white together. The muon goes off on its own and becomes a sterile muon, and the white turns into showers. It's exactly what we have here. Now, Neil says that I should be looked at and spoken to and taken into account these, and be peer reviewed on this. And I have not been able to be peer reviewed. And as a matter of fact, I went back and forth with Don Lincoln quite a number of times. And eventually he said, don't ever contact me again. And never looked at it to my knowledge. He just said the first things out of his mouth was, oh, that's just reflection or something. I forget what it was. He just had all kinds of stuff. But I said, they're the same particles you found. These are the same particles. There they are. How can you possibly miss them? We used light. When we accelerated light, that's light accelerating. Not only did we see the light accelerating, but let's just take it from the top. And again, I'm going to try to be respectful, but I tell you, this is going on forever. This because I contacted him, I think it was 2014, maybe 2015 tops. I think I went to University of Geneva, 2016 maybe. And I told them exactly what we're doing. And then they shut CERN down for 3 years to upgrade to use CMOS, because you could see it. I mean, this is fabulously perfect. You can see every little detail. Now, this is the wave just beginning to accelerate. You wouldn't see anything at all here. You would see nothing at all, I don't think, until the particles started to accelerate. You see, back here it's not accelerating. It's still just, but it's here. It's got to be there. There's no question the particle is back here somewhere. But just all of a sudden it's starting to accelerate. And as it accelerates, it pushes these particles, and the field to field causes this wave. The particle's in the center, the wave is out here. But it only is when it's going forward. When it's just sitting around, it just has a field around it, just banging around doing nothing. It has to be light, moving. So something had to send that light out. All right, and we use a red laser. All right, and there it is there. Now, there's the particle. You see that little white beam? All right. This is the particle actually being pulled out of the magnetic field. It's unheard of as far as I know. And here it actually concusses with its own self. And why would I say that? Because they can't get through the venturi freely. The venturi is a restriction. And all it is like a venturi that restricts, very tuned, so that only the white can get through here, and the black is not allowed through. And the black bounces back, and the white, a lot of that bounces back as well. So by the bounce back, these particles here feel like they just hit a wall right here, just as these do. Now remember I said before you wouldn't see these fields? You wouldn't see that field unless it was accelerating? You don't see that field, you don't see this field, you don't see this field, you don't see this field. They're here. That's coming this way. That's coming this way. That's coming this way. That's coming this way. You never would see it. Why do you see them now? Why do you see this side of it? Because it's going backwards. Energy smashing against other energy causes it to glow. That's what glow is energy smashing into some other medium. And here it's glowing because it's banging into its own self. As it's going here, it's turning into what they call the neutrinos. It's not quite fully fledged photon. Here it's full-fledged photons. And normally you wouldn't see this, except for the super colliders. They see them just like we see them. But we see them because they turn into photons here, thinking that they just hit a wall, and they're bouncing back. That's when they turn into the photon phase. Otherwise, they're neutrinos. And these here, you don't even see these. You see, there's nothing there at all. But they're there. They're coming through here. And now because they're getting bashed backwards, they're doing the same thing this one's doing here. They think they just hit a wall, and they're going to bounce back, just like normal light would. It would bounce back at you. Boom, boom, all of this stuff. There's light coming at everything. Everything here is light bouncing back at you. That's all it is. And light has a field surrounding it. It's like a balloon. It hits it, boing, boing, and bounces back. It depends on how fast the light's coming, first of all, and then what the nature of the texture that it's hitting, how much you're going to see coming back. That accounts for colors and brightness and all that stuff. Very simple when you if you understand the particle. The particle is just like a basketball. All right, so you saw the particle coming through the air, just starting to accelerate. You saw it full acceleration. You saw the explosion. And that's literally a subatomic nuclear explosion, subatomic. Now, you saw that this is the same particles that Fermilab has, and CERN. Now, I talked about neutrinos. These are neutrinos. You see that? And the only reason we can see these, they're all up in here too. They're everywhere around here. But the only reason we can see them is because they're starting to get bright. And the only reason they're starting to get bright is because they're backing up against the photons. And the only reason the photons are here instead of when they bounce off the wall is because they're right in the exact stream to hit the venturi. That's why we can see these changing into neutrinos. Up here, you see, they're changing into neutrinos. Here is the reverse cusp wave coming back. And that's where all this whiteness starts, from the pumping back from the venturi. But these are all neutrinos. They're not fully fledged photons. These are the only ones that are fully fledged. The only reason we can see them is because they are right at the venturi. They think they hit a wall. That's light bouncing back at you. This is not light bouncing back at you. That's light traveling. Neutrinos are traveling photons. And they just don't have the energy of the photon. Photon only has that much energy because it thinks it hit a wall. See the green? Exact same thing. Exact same particle. And these are the neutrino values. But the green is much faster and much more powerful than the red, and the blue is much more powerful than the green. This is fully understood, the different colors. The intensity of them, the frequency of them, which, as a matter of fact, these are the visible spectrum, the different colors we see. But as they go from the short, these short waves up to the really, and then they get up to something they call the ultraviolet catastrophe, where at the ultraviolet range, it's going so fast that all the white particles go flying off, and all you have is the gamma radiation, which is the black, devastating smackers left. You probably got a bunch of the little white ones too, but mostly it's going to be the smackers. And that's right up in here. Gamma rays. They call them ionizing. Well, they're ionizing because when they hit something, they throw a bunch of electrons out because they're just nothing but smackers. And those are the things that kill you. All right, so here's Neil again responding to Terrence Howard, and this is from Terrence Howard's paper. Now he says, page 2 in here, he mentions people he declares were persecuted. He should be talking about Velikovsky, but I am also persecuted, so I want to be on that same list.
Their vision exceeded the myopic view of their contemporaries. And he mentions Walter Russell, Nikola Tesla, John Keeley, and many, many more. Regarding your list of people who have made brave sacrifices, I note that to be a genius is to be misunderstood, but to be misunderstood is not to be a genius. The work of Russell, Walter Russell, has eluded any experimental support, and the work of Keeley is generally not reproducible.
I can tell you one thing right now. I'm sure nobody tried to do what they were doing. You can only do it for so long and present it for so long. Nobody else does it. Well, what does that do? Because there is no peer review that's reality. It's peer review to support your side of it. Now, if Neil will discuss things with me, I have shown you or will show you that I think his whole concept of reality is wrong. So that's where I'm coming at. Neil, you should be talking to me, my friend. And I'll be very respectful, just as you're being very respectful to Terrence Howard. This is nice. I like this kind of interaction.
Science is about reproducibility. I can have the most brilliant, crazy, fun idea ever, and if I perform an experiment and no one else can duplicate that experiment, it belongs in the trash heap. It's me in my own world, thinking I have landed on an objective truth, when in fact I haven't. That's how
this is as Dunning-Kruger effect works.
Science works. The reproducibility of results.
All right, so, well, let's see what he has to say about Tesla.
For the work of Tesla, much of it had very real value to physics and our understanding of electromagnetism. And that value is duly recognized by my community in the naming of a unit of electromagnetism after him. You can't get more badass than having a unit named after.
Yeah, after you're dead for 100 years. I mean, this is the problem. They will not listen to anything and they will not respond to any evidence whatsoever. I have found a zero. Now, if Neil is different than the rest of his contemporaries, he will respond to this. And Terrence Howard absolutely should respond to me. I don't go along with your mathematics, Terrence. That's just sort of a little fluff that didn't work out for you. You know, I appreciate you thinking outside the box, my friend. But sometimes you can't just make things up. It doesn't work. This is reality, what I'm talking about. I show reality. And not only am I going to show the reality of the things that I present physically that are in his realm, that he should correspond to me. I present the things that are in our ancient past, which is the mud fossils. And that changes literally everything. Between the physics and the mud fossils, there's virtually nothing that isn't changed. Chemistry, physics, what's in space. Space is saturated with particles, absolutely saturated. Light slows down, it's not the same speed forever. We can accelerate it, so we know we can accelerate it. That's just totally not allowed, absolutely not allowed under Neil's way of thinking. I'm not positive. I'd like to have him respond to that. I say, Neil, you see the light accelerate. And if you don't see that, I don't know how you don't see that. Because here it is. And then it accelerates and pulls itself right out of its own magnetic wave. And this is the particle. And we use CMOS. And I have other people that have done this. So it is reproducible. Let me show you what another guy did. This is Rod Warren. And he did this for, got to be 5-6 years with me. And finally, I can't get through to him anymore. And I think he just gave up on this because he just can't get anywhere. And, you know, this is from my atomic flood theory. I need to be able to show all of this, which I can. And sooner or later, Rod will be recognized because he was the one that discovered this venturi just by accident. Total accident. He had no idea what he was seeing. When I saw the output of this thing here, I said, "Whoa, Rod, let's talk." And we did, and he was so gracious. Anyway, he'll get his comeuppance. The denial by science, as far as I'm concerned, is strictly in the interest of funding and lining their own pockets and, self-interest. That's all I've seen so far. Now, Neil might be different. We'll find out. All right, here's Fermilab again. Now, this goes back a ways, so I believe they still believe that this is the most successful theory ever, which is the standard model. I say this is not successful. The W and Z particles are the only ones that exist, and then everything else is made of those two particles. And you see they show the Higgs and all these different quarks and leptons and all these things coming out of it. Well, let me show you ours, and I'll show you those two particles, and then I'll show you all the Higgs. All right, let's just say this is what they're doing at CERN, Fermilab. And they get all this particle zoo. All right, and this could be this big. This could be this big, one. This could be a low energy photon. This could be a high energy photon. These could be just the little bits and pieces of particles. And that's what they're looking for, is the smallest bits. And they see all these and they say that's a particle zoo. And we got leptons and quarks and bosons and this and that's. And now, so this is what it looks like in this artist rendition. And I say it's nothing more than these hitting together, just be splashing particles everywhere. Now, this is what it looks like in their little doodle about this. So here they're coming together. They see blue particles, which are very high energy particles, and then they see the greens and the yellows, and the reds don't go so far. They sort of hang around. Why is that? Well, the red is the weak energy that's right on the outside. The blue is way down on the inside, attached directly to the dark matter. So it does not want to leave, but once you can make it leave, it goes and it doesn't come back. It's just extremely high energy. All right, you see this? This is my proton. Their proton is like one big positive thing, and the tiniest little particle that, well, actually the proton doesn't have any particle attached to it at all. It's the hydrogen that has the particle attached to it. But a proton would be just one big positive chunk, and it's not. A proton is a big ball of dipoles, just like this. They're all little tiny magnets. Now, the black core goes to the center. So the blue ones that are right down onto that black, they are tighter than hell. They don't want to leave. The green is pretty tight, and the red is sort of just floating around. So when this explodes, the red sort of just hangs around and the blue takes off like a rocket ship, because in order to make it dislodge, you have to really have a lot of energy. And the same thing the green goes to, but the red sort of hangs around. That's why they show their Higgs. This is the anatomy of a proton, and it consists of 1,823 dipoles. Neutrons are 1,824. And then I'm saying these are the only two particles that exist. They're the black and the white. That's all there is. All right, there's going to be differences in the standard model. And these are the changes in science: chemistry, space-time, redshift. We're thinking that we're seeing light that's going a certain distance and everything's expanding. And no, the light is slowing down as it comes to us. Let me just show you something about the universe. All right, so anyway, this is my model based on the experiments. This is the phone that took all these pictures. It's a Samsung Galaxy S3. This was released in 2012. And when Rod apparently got that phone, he started taking all these pictures, and he was blown away by the pictures, as I was too. He didn't realize what he was doing. He was trying to do a double slit experiment, and he used nails instead of like a flat plate, and it caused a venturi. Very simple thing to do, and anybody can recreate it. And another guy, Fabian, did it, and he did two lasers at the same time, the blue I mean the red and the green. And it shows the different, well, I'll show it to you. Now this is Fabien Boulay. I believe he was in France. And this goes back a long time ago too. He put both the green and the red laser through the venturi at the same time and took it from the side. Now, I don't think he has the same phone as Rod did. I think that Galaxy S3 is unbelievable depicts. And the other thing was, Rod was using the selfie side. He was using the selfie side to take these shots. Now, I did a bunch of them too, but I was just terrible at it. And I work in the Mudfossil realm, the exceptionally preserved soft body creatures, which I have DNA tests and CAT scans and everything. Same thing there. Not allowed because of peer review. So I don't have time to do much more with this, but it's right here. How much can you do and just have it ignored? The green is coming through hot. You can see it, and it reconcusses out here. The red just gets pushed out of the way. And it makes the particle, instead of spinning the way it normally spins this way, it's making it spin like a barrel roll. See it? You see them barrel rolling? That's not normal. Normally they spin this way. Even if they're going up in an angle, they still spin in this direction like that. They don't spin like that. They always spin polarized to the Earth. That's why they call them upspin and downspin. Well, this is circle spin, so that's something new. Now this is CERN showing what they get for Higgs fields, and then they pick through all this debris to see what they can find. Well, why don't you start with the littlest ones first, which we did, and then when these Higgs fields show up, it's because the white, which is all by itself now, reattaches to a black. You see that little sizzle coming up there, zzz, bang, and it hits there, and they just spin. They're all coming out and whacking into something and making them spin. Now, there has to be a whole lot of extra black over here, as far as I'm concerned, because think of it this way now. Let's look at this carefully. You know that the light accelerates, it divides right here at the venturi, and then it fuses back together. So this is fission, that's fusion. Let's look at it here. This is from the big guys. This is not me making this. They say you have a muon neutrino, the black one, you have the electron neutrino, the white one. When they hit into heavy water and so forth, they split. The black goes all by itself. It's called a sterile muon. The white turns into showers. And these have extremely high energy. Now, that is exactly what we did here. The black separated right here, and then they're all by themselves. The white showers, just like this, all these cones. Now, you can see the black. You see them? And the black, they'll get right on top of each other. They don't care about being right next to each other. No problem at all. And you see how there's a whole batch of them just waiting here? Where'd they come from? Where did they come from? They are being separated back here, and only the white are coming through. So don't forget, coming into here, you got a set of black and whites coming in, and the black ones are just they can't get through. The white ones get through, and then all of a sudden the black ones are back here waiting for them. How did they get there? Are they just laying around, extra black ones? I think so. I think there's extra black ones just laying around. And they want to be attached desperately to that white. So they jump right back together. See around the edges, they're jumping right back in too. But this is dark matter. So you don't see that dark matter until it's laying on top of the white matter. You see it? You can just barely see them here. You see them, but when it's laying on top of the white matter, you can see it. Otherwise, it doesn't emit, it doesn't absorb, and it doesn't reflect. But in the dipole electron flood theory, it is the core. It is the core of every single atom. And all we can see is in the atomic realm. We can't see subatomic particles. You know, if you see them, they're just in debris. We see them because they're light. That's as best as you can get right there. There's no better, because we started with light, we ended with light. And when these came in those fields, when they come back together, they create new fields. These are Higgs fields. When they're coming this way, they're also Higgs fields, but they're not reattaching Higgs fields. They're sort of creating Higgs fields in waves. These are reattaching and creating this similar look to them. All right, don't forget, these are the waves coming this way. You see them? Coming this way. This is not Higgs fields yet. Well, maybe they are, I don't know. But they're coming through. They look like Higgs fields to me. Because when you see the Higgs fields coming out the other side, they're looking at just about exactly the same. This is when the white smacks back into them and they create back into those same particles again. It looks like to me. Let's go back one more time. All right, we just showed all these fields coming. And when they're approaching, they're the same fields. You just don't see them. So it's field to field, ashes to ashes, dust to dust. All right, so just think about this. These are the particles that Fermilab's talking about. I showed you those particles. And here they are right here. These are the particles. Those are the particles I showed you. The same characteristics. They act the same way. They have the same weights and so forth. Standard model, I show you, the only particles that exist are the white one and the black one in my model. And the Higgs is from, we have Higgs on both sides. They throw all these other particles into their particle zoo. And here's the quantum foam where space isn't empty. No, it isn't empty because light particles are particles. They're matter. They're out there. They're matter. And let's look at them out there. All right. They're looking for quantum fields, they call it, in space. You see that? That's a black ball. And you see this one over here? That's a white ball. You can hardly see it inside their field lines. You see? And these are the tightly held fields, and they get wider and wider and wider as they go out. I agree with this exactly. That's a dipole, and this is space. Now, light going through these fields will be affected. There's no question whatsoever. And space is saturated with these fields, and these fields consist of particles, basically. They're being particles emitted in magnetic waves. And here they are in our neighborhood. That's a picture Rod Warren's nephew, Dylan Carpenter, took. He's in New Zealand. And and he got a new phone, and I don't know, he's got some kind of app, and he just gave me one picture. Well, he gave me a bunch of pictures, and then I've never heard from him since. And I can't seem to get a hold of him. So I don't know how he did this. But I can see it's exactly what I expect it to be. There's something back here that's creating these big fields. This is the moon, which has no field. The field you see here is part of this field. The moon is not spinning, so there's no field. But it is moving this way, crushing light, turning it blue. And here, shifting it towards the red. All right, now here, I have no idea. Now, this also he took, and I believe this is Venus, because Venus spins one direction, and it goes backwards, let me put it that way, spins in a backwards direction, and it looks like it has two fields. You see this heavy one and the light one out here? They're both on the same pole. Now, plus, this looks a little strange here, too. But you see it coming straight up the center and out? That to me looks like it has two fields. And that might happen if it was going the same way we're going around the sun, but it's spinning in the reverse. So one field is from the sun interaction and the other is from spinning, something like that. I'm just guessing. And it's just a crazy guess, but it does appear to have two fields. That's the only one I see. Now, I believe that is the Pleiades. 1, 2, 3, 4, 5, 6, 7 sisters. And they're all fields are intertwined with each other's field. Again, this is from Dylan. I don't know what to say. I can see they all appear to be dipoles. And this is where the darkest side is, and this is where the light side is for some reason. It's a polar sisterhood. I don't know what to say. This is where the dark is collected mostly, and this is where the white is collected. That's polarity to me. And you can see the field comes right down the center. So this is a globby field on one side and a globby field on the other. That's what I'm seeing. All right, everybody always asks, how do they do this? It's very simple. You take two cylindrical devices here, or you could have 3 or 4, or however many you want. But to get a nice, clean, singular pattern, you have 2, and you shoot your laser right down through, right in exactly here. Now, it's got to be tuned correctly. And it'll, if it's done right, it'll collect here and bounce back everything and only let the white through. So they're 2 like barrels sticking straight down like this. Now, if I was going to do it again, I would use a caliper, something like this, and round or venturi it in. So all it is a restriction. Like you could have 2 coming out this way. All it is a nozzle. That's all it is. And the tighter you restrict it, the more energy you're going to get out here, and the more acceleration you're going to create here. That's why it accelerated. It didn't accelerate for no reason at all. You see this? If there was no venturi there, that's not going to happen. This happened because there was a venturi like this right there, sideways. So the light had to go through this slit, but it was angled this way. So all the light that would have normally gone this way now has to go into that little device there. It's just like if I took this out and I put it here. All right, like this. The light's coming through. The tighter I make that restriction there, the less light is going to be able to get through. But the white will be able to get through when it's really tight. And you want it to funnel down so that it forces the waves into each other. The white particles hate each other. They want to get away from each other. So when they bang into each other, that's why they glow. It's white to white is the glow. The dark matter is just a carrier. That's not. It doesn't glow at all. You see, and it pushes. You see it push? That's the black pushing the white. Now the white bangs into everybody else's white out here in a ripple effect. Ahead of, like this is just as the light's starting to glow. Now, again, Rod Warren did all these shots, and he must have taken literally thousands, I'm not kidding you, and I'm not exaggerating whatsoever, thousands of hours doing these. And he did a magnificent job, and he will be remembered for this. Now, that's the subatomic explosion through the venturi, and here is the product coming out. All right, some of the black comes through this time. Primarily it's the white. You can separate some black, some white, and they'll eventually make their way into those Higgs fields. And they'll be like this. Now he's the master. He's the master. Now you can play around with it. It's not, like I showed you, it's very simple to do. You know, because normally the double slit is a flat plate with 2 slots. And they say the light coming through overlaps each other like waves. No, it spins in a circle. Let me show you. And he clearly shows this. All right, I showed you how much faster the green is than the red, how much more powerful it is. It just pushes the red out of the way. Now let's take a look at the blue. Here's the blue. It's coming in out of the venturi hot, slowing down. So here you can't even tell there's 2 dipoles. But in each one of those little balls, the spinning so fast you can't see. Now they're starting to spread out because it's getting slower and slower as it travels through the air. And now you can tell there's 2 particles. All right, but really it's the blue, you can't do much with it. It's just too hot to handle. Let's put it that way. Now, the green and the red is pretty simple to see. You can see it right here. Very simple. It's nice and slow. Boom, 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 boom. Neutrino. And these are different styles of neutrino. They change flavors, they call it. And this is understood. And then they see the photons, but they only see the photons when they collide them. You can't see a photon unless it bounces. Now, I showed you that. Oh, I didn't show you this. This is what light does. Now, they say a double slit experiment. It comes through two slits, and it's a wave. And when it hits the other side of the slit, the waves do this kind of thing. And that's why you get all these little lines. I say, no, that is not correct. As I just showed you with the blue, light spins. You can see it spinning. You see this? It's spinning this way. It means it will drift to that way. Slower and slower and slower. It's drifting to that direction. But it's spinning to this direction. So we know that, and I show you a ton of them spinning. The red you can see very, very, very simple. But this is quite simple too. Now, this is what light does. It spins in a circle. So why would you see this effect? This is like a drill bit. You see that? Now, I don't know whether this is a single slit, a double slit, whatever number of slits. It doesn't matter. Rod was working with real tiny ones, bigger ones, wide ones, narrow ones, all kinds of different things. But I can tell you what this is right now, whether it's a single or a double, I don't know, it doesn't matter. The light coming down here is spinning in a circle. You see it? It dives down here. Right? It bangs down here and it goes under and over here. Somehow it's like a drill bit. You see it? And when it gets through the other side, the white particles are so energetic, they push each other apart. And they create these elegant little patterns. That's not nothing. That's a serious separation of power. You see how intricate and fine it is? And then there's like stability states, and then there's areas in between that are not quite as stable, but there's big ones. And you know, I haven't figured this out yet, but because there's a whole batch of them coming. It's not just one. They're coming over here, they're coming over here, they're coming over here, just like I showed you before. But once they penetrate the venturi, then they're on the other side, and this is what they come out as. Extremely interesting to me. How detailed that is. You see that? That's a drill bit. To me, it's quite amazing. But when you think about what's happening here, it's spinning all over the place. But most of the spins are going to be going through the center. And that's where you're going to get your main reaction. But these follow that pattern just as incredibly as it could possibly be. But anyway, the light does spin, and this is the result. All right, I think I might as well wrap it up with this. It's as simple as this, and you're going to have to do this yourself. Somebody's going to have to experiment. Rod did this. I'm not going to do it again. What's done is done, and if somebody doesn't reproduce it, well, it's done. These are the particles coming through. They're pinched in the venturi, and all that is two pins straight up. And he used nails, literally finishing nails, the first time he did it. And I think he used 2 or 3, I'm not certain. But what he ended up with is this. This was one of the first ones I saw. And when I saw it, I just went off the wall crazy. And I got a hold of him, and it was so nice to help me for years, and nothing, absolutely nothing for him. But is Rod Warren from Australia. He's got to be recognized for this. Now, this is the dark matter. That is black. This is the dark matter. And this is the energy. It's got all the energy. This is what you want to put in your car to charge your car up. And here's how I say it could be done. Don't forget, this is nothing more than a venturi shooting light down here. And when it hits the venturi, this is what happens. So this is the deal. It's coming down, it hits the venturi. Then what happens? Well, here it comes. At the venturi, the black gets popped back out. The white goes through. Now, there's going to be a certain distance, like right out to here or so, where you get these showers, and they get intensely unbelievable amounts of energy, and I'll show you that in a second, the statistics on it. Now, right back here, they just recombine and become nothing more than light again. As I showed you, it seems like Higgs to Higgs. They come in looking like Higgs, they come out looking like Higgs. But in here, you have all the energy. So what you need to do is to create a solar harvester here. Just like a solar collector, only the real good ones, the new stuff, they have like a, you know, it's all CMOS based, but it's thin film, perovskites, I believe they call it now. It's not completely done, but you could still use a solar collector, I would think, because you're increasing the energy value here significantly, and you have to send this down through a photodiode into a collector, Now, and then you just use a little bit of that to keep it going. You should be able to create enormous amounts of energy. And if you could, it would be simple as something like this. A box like that you could carry around, watertight, all by itself. Once it started off, it just keep going. Plug anything you want into it. Harness your car into it, your house, whatever. And you should be able to have thousands and thousands of these inside of this. And every one of them creating strictly white juice. And that is the juice that you want in your car. Right now, you have to rip it away from the black, which requires literally, and I'm not kidding you, I think they claim a ton, an actual ton of force to rip the white away from the black. And that's what you have to do now, to push that white down into your car or into any battery. If you know what a generator sounds like, when you start it up, there's a motor, all right? There's a motor, and that runs a generator, which is the electric part. So that gas engine goes, it's just running, nice, perfect. You flip the switch to use that energy, and all of a sudden you're going to hear, it's fighting these fields to take that energy out and send it out into the grid. That's a motor generator. We didn't have to do that. It separates all by itself. No extra energy input to do that. That's serious. And if it works, it could create this kind of energy. You see this there? This is the physics of electron showers. And I showed you, just let's not get confused, this is electron showers. Electron showers. Electron showers. We did it. Electron showers. Now, the physics of electron showers, are they any good? Well, I think they're pretty good. They use the protons. They have to get hadrons and all this nonsense and decay to hadrons and We started with neutrinos. They had to create these neutrinos and antineutrinos of all flavors. That's fine. And then it bumped it up to 100 giga electron volts. That's billions to a few trillion electron volts. Increased energy is enormous. I'm pretty sure. If I'm wrong, I'd like to have somebody tell me. Neil would probably know. But right now, I think this is about as good as you're going to get as far as understanding the subatomic nucleus. This is coming right out at us, and these are the Higgs fields. They're being created as these particles are whacking. See one coming right out there, bang. They come out and create these fields. They don't want to be alone. This one, I think, is a reverse spinner. And it hit one of these other particles and made a backward spinner. It's the craziest thing I've ever seen. And if you're a physicist and you want to see it, you're going to have to get a hold of me and I'll show it to you. But I believe that right there is an anti-photon. What that means, I'm not sure. But they spin. They have a spin to them. It's a spin like this. And that's maybe spinning like this, drawing an energy into itself. I don't know. Nobody will ever know if we don't start looking into this. All right, here's a little more mind-blowing. This I saw in about, I think it was 2015 or 2014, somewhere around there, where the Russians were out in space and they injected some charged particles into a vacuum chamber. It means there's nothing in there, but these particles have a charge on them. That means they have extra energy. When they started to settle down, they formed literally a black hole. This, in space, there's no crushing effect. Here on Earth, all those particles will want to get to Earth. In space, they all want to get to where there's the most dark matter. Earth is just saturated with dark matter, and there's no question about it, because static electricity, bzz, right to ground. What is ground? It's got all the extra dark matter. It wants any electricity, lightning, bzz, go right to ground. Static electricity, right to ground. Electric power, right, it wants to find dark matter, and the Earth is saturated with dark matter. All right, that's ground. Ground is where the dark matter is. All right, so we want to collect all that white and be able to go through tubes and so forth, which is wires and conductors and motors, and then end up getting to that black. Because it'll go there, and it wants to go there with a vengeance. That's what electricity is all about, is to get the white heading back to the black. And here it is right here, the white separated, and then the two of them matching back together. And if we can get in between there and get that white, I think we can power a lot of things. Because it's a whole thing in life is to get back together and be stable as a Dirac neutrino. The Dirac is, they call it matter and antimatter. It's not really. Well, you call it what you want. That is, to me, is dark matter. And this is gravity. Because the white wants to be attracted to the dark matter. Gravity is the dark matter of the Earth attracting everything, because everything has white. Every single piece of matter is, to my way of thinking, basically an equal number of black and white. Sometimes they're separated into a magnet. Sometimes they have poles that are offset, which calls dipole moments. But they're all sort of an equal number of electrons, which are the dipoles. Now, heat pushes more of these in. Heat is nothing more than these particles going in there and just floating around among the other particles, because they're more wanted inside of something than they are out in the air. It's like you're hot air, they're going to push into you and make you hot. It's just like Caesar here. He's sitting around here in 60-degree temperature, let's say, in this room. And all of a sudden I turn it up to 80 degrees. He's going to want to absorb some of that energy to offset the 60. So he's going to take in and get to be what they call ambient temperature, which would be 80. So heat is nothing more than these coming and going in small, easy ways. It's like a real low end of electricity, because these are electric particles. So heat is nothing more than electricity, you know, on, you know, a slow step. Electricity is these on steroids. It's all electromotive force. It's the voltage. It's the pressure. All right, and on Caesar here, the pressure is not going to be much. All right, but if I put a laser on him, yeah, it's going to burn right into him. The pressure is going to be a lot. It's really not hard to understand once you understand the concept of dipole electron flood theory. Everything's made of the same particles. Everything there is made of these particles right here. Every single thing there is. And that one right there is what they call a gluon, and the two of these together is a photon. You separate the two of them, you have a muon, a black one, you have electron neutrino. It's as simple as that. And that's all there is. So all this other stuff about the standard model, these are the only two things that exist, those two right there. When they come back together, or you're in the phase of making them big, they're Higgs. I show you when they're coming into the venturi, they look like they're Higgs. When they're coming back out of the venturi, they look like they're Higgs. In between, they got the white and the black separates, that's all. A gluon is nothing more than two of these together. And a photon is nothing more than two gluons back to back like bar magnets. All the rest is just superfluous, not necessary, but you can look at them. They're just states of matter in energetic areas. Now, to think that we're going through space and there's nothing that's going to slow down light coming at us is crazy. It's just not correct. So everything they're doing about measuring, well, we can see back to the beginning of time. No, they can't. It depends on how dense what they're looking at is. All right, you might be able to see back further if you're looking for here, but not if you're looking through here, or over here, or over here. You're going to be just, it's going to go boom, 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 boom. That's what's going to happen to your light. It's not going to go zip and never slow down. And as I have shown you, unquestionably, we can accelerate it. No question whatsoever. Zero question. And we can see it slow down. Zero question. And CMOS is the cat's meow as far as being able to see these things. CMOS is designed to see these particles, but not the big chunks. CMOS is not designed for this. And this is what CERN is doing. So they got big bombers. These things can be absolutely enormous. All right, because they're hitting head on with these things. So they might get a chunk this big. And as the CMOS is totally destroyed, we never can get anything bigger than that. It can't be bigger. So we got these, because we started with this. They're not going to add together to make a big ball. All right, I hope you understand it. We can do the CMOS. They could not at CERN. So they went ahead and upgraded. And I think they just came back online. Hold on a second. All right. Terrance is sometimes, he's coming up with some things I don't agree with, just like Neil doesn't either. But I'm showing the things to present with actual evidence. And my thing is transfer of energy is from light into an atomic vapor, which is like a mist, and it congeals into matter. That's what matter is made out of, light. It literally is made out of light. And I long ago said Rutherford's atom was wrong. Rutherford's atom is wrong, which means the Bohr model is wrong. The Bohr model is what the standard model is based on. And here's what I had. It was two types of energy. There was dipole-dipole interaction. Some of them were polar and some of them were non-polar, depending on what the configuration of the centers. Like bar magnets are obviously quite polar. Most other things are just not polar. They don't stick to anything or repel from anything. Everything's sort of mixed together. And this was, I did a lot, if you want to talk about doing calculations, doing this and that, this was my paper proving everything I was talking about. To my mind, it proved it. Nobody would take a look at it. Who would look at it? Nobody looks at these things. But I did this, I did more of this probably than anybody that was in this time frame, because this was when everything was all of the different theories were being tested, and they had all kinds of new equipment they were coming up with, which is all the stuff I worked with. Here's another one, dipole moments, bond polarity and the shapes. Everything was dipoles, because everything is dipoles. And then you have to know all about the different rules and laws and all this nonsense. This is where it didn't work. I told him, I said, this stuff doesn't work. Nobody wanted to hear a word. So what do you do about that? If you don't say the same things they say, they don't want to hear from you. So if Neil thinks that I haven't done my homework, then he hasn't watched. Because I'm in chemistry, all of the different principles and energies of the chemical reactions, and that's some pretty serious stuff to be. Anyway, I did it all. So, going to once again sort of, listen to what he has to say.
Produces art, sculptural art, which I find to be intriguing, even beautiful. To me, more intriguing than beautiful, because you got to look at it and you keep looking at it, like, what is that? And what's going on there? I just want to read you my ending comments here. I could not follow the reasoning on these last few pages, but the illustrations that derive from them are beautiful, regardless of how they were derived. My notes have been strongly critical of your reasoning and conclusions. I was candid and blunt out of respect for the energy you have clearly invested in this work. But if you're sure that you are still right and that I have completely misunderstood your thesis, then you will need to look for another person to evaluate what you have done and solicit their comments.
Well, I am looking for you, Neil, just to have comments about my work. I think that's fair. I think that's totally fair with your statements saying that that is what science is all about. That is science, is to review material evidence. Not this nonsense with all these numbers and all that nonsense. Forget that. Material evidence, which I show. My stuff is not nothing. My stuff is this. And this is all pretty well understood now. And they're starting to come around. I see every day now they're starting to come around. But this is a big shock to the physics community. To have somebody like me come in from outside and change everything. And it really does change everything. And that's why Fermilab, I showed you the Fermilab particles. You saw, it's exactly the same stuff. It's exactly the same. I got a hold of them when I got a hold of the Russians. I think it was 2014, 2015. And I got a hold of Don Lincoln. I said, Don, I think I found your particles. Here they are in our light experiments. And instantly I got a return. Oh, no, that's just refraction. And I said, well, let's take a look at it. Will you take a look at it? And right away, no, that's just nonsense. You can't see that. It's impossible. Blah, blah, blah. I said, no, well, Don, let me show you. Here they are. This is it. Here they are. And it went back and forth for a while. And finally, he just said, don't ever contact me again. And that was it. And I think I'm showing exactly what he was showing. Only we could do it without having all this billions of dollars in government funding. And I think we could spend our money in a much better way. These are the particles, the exact same particles that they found at CERN and Fermilab. No difference whatsoever. Only we can see them as combined particles as photons. Then we can see them as divided particles as muons and electron neutrinos. Here they are combined as a photon. Here they come apart. Now, Neil says he's a scientist and he's open for all new things. Well, this is new, my dipole electron field theory, and it's backed by solid evidence. And so are the Mudfossils, which is also, I'm sure, new to him. But to the general public now, it's not new anymore. It's starting to be understood and accepted. But academia, once again, it throws them into upheaval. Pretty much destroys geology. It destroys the history of when the Triassic era was created, the red bed, the gray clay, the black cap. all the timelines of history and archaeology and mankind and so forth, completely different than they said. It supports everything that Velikovsky said about us almost being impacted by Venus and the actual waters of the Earth boiling because of this enormous amount of energy almost hitting Earth. And it literally stopped the Earth from spinning for a short time. And then it would start back up again because it's scrubbing through the universe against our field. And it just, as it rolls around the sun, it would start back up again and start spinning. They said it stopped for a day. It just basically stopped. There was a full day of darkness and a full day of lightness, and then it started to spin back up again. And these are all things Sagan said, oh, I couldn't spin back up. Absolutely it would spin back up. No question it would, because of the sun's light hitting the Earth and creating that zone which would interact with the zone coming forward. It would start to spin it again. And that's exactly the spin that it spins, just like that. And it's only going to get to a certain speed because it's only spinning according to how fast it's hitting the oncoming atmosphere. That's why the days are pretty regular. Now, they may get a little shorter, I would say. As the atmosphere gets bigger, it's going to be pushing harder on the side. In other words, here's what you got. All right, the Earth is going around the sun. The sun hits here. This is where it's dense with particles. It's fluffed up and hot. So as the Earth goes this way, as everything circles the sun, this zone here is where it's going to be denser. This is going to be cold, and this is the air is going to go by easy. Here it's going to be hit, so it's going to spin it this way. And that's exactly the direction the sun spins. The Earth spins. And it will spin as it just keeps going. It'll start to spin faster and faster until it hits a constant basic speed according to the speed of its orbit. All right? So, it'll start to spin faster and faster and faster, and then it'll get to 24-hour day, and that's it. Okay, now Neil's moving into how the Earth works. Listen to what he says.
Was not because people were stubborn. It was because people are cautious. Any new idea needs to be put through the ringer. That's how science works. You put it through the ringer. Every possible test you can. Not just because it happens to look like South America fits with Africa. Any better evidence than...
You see, he's talking about continental drift and seeing things in patterns and so forth. I'm sure... Well, let's hear what he has to say.
Oh, wait a minute. Fossils matched between the west coast of South America and the east coast of Africa. Not recent fossils, fossils from millions of years ago. That's interesting. Things that make you go, that brought some more people over to the camp. You keep that up, and you reach a point where enough evidence is brought to bear on the question, and then you have a new emergent truth. But
all right, well, this I have done, Neil. Almost 10 years ago, DNA, CAT scans, specimens, body parts that are just astronomically large, and they are so astronomically large that you guys and your peers, I don't know about you, refuse to examine them. Now, if you're good to your word, and this is going to be a stain on you if you're not, my friend, because these are the kind of words I hear from everybody, not just from you, and they just don't ring true. So let's see if you or Terrence Howard will confront my evidence. Now let me show you. You're saying, you got a brand new thing if you can bring enough evidence. Well, the evidence is fine, but if nobody looks at it, the evidence means nothing. It's zero. So will you look at it, Neil? That's what I'm asking. Terrence, will you look? Can we have a discussion? Joe Rogan, will you let me be on your show? Will you let me explain these things and show you my evidence? I've tried to get on to Joe Rogan's show, and I've never gotten any response from that either. And I'm pretty much blacklisted because I was one of the first to be speaking about these crazy, crazy ideas. And they are crazy, but they're true. When something's true, I don't care if it's crazy or not, it's true. All right, let's let him finish off. And you know, I can be very respectful, but you have to pay attention to the things that are presented. So far, that's not happened.
To the camp. You keep that up, and you reach a point where enough evidence is brought to bear on the question, and then you have a new emergent truth. But at the vibrant energy that goes on at conferences and the contest of ideas, that's how we roll. That's how it works. When Einstein came out with relativity, saying space-time curves, Al, what are you saying? What are you doing? Well, you can test it with the total solar eclipse. So the idea comes out in 1915, is published in 1960.
All that is gravity. That's only gravity. The particles in space and things their light is warping around these masses. So he's talking about a total solar eclipse. The light coming at it is going to warp around. It's just natural. Gravity pulls everything towards it. So that's nothing. Sorry, Neil. We need to talk.
1919. We measured light around the edge of during a total solar eclipse, because you can't see the stars during the daytime. You see the light rays bent from their actual coordinate positions on the sky. Sir Arthur Eddington, an astrophysicist, provided the first experimental evidence for Einstein's general theory of relativity, which, by the way, was published in a peer-reviewed journal. Crazy idea.
Yeah, peer review, it just doesn't work. It doesn't work, Neil. You have to say what your other buddies say. And I'll be just amazed at if you respond.
The platform to be accepted for the ideas is not social media. It is not Joe Rogan. It is not my podcast. It is research journals where attention can be given on a level that at the end of the day offers no higher respect for your energy and intellect than by declaring that what's in it is either right or wrong or worthy of publication or not.
Exactly. It has to be examined.
I wanted to post this to my website so you can see my comments mixed in with his treatise, but you got a sense of it. Thanks for listening.
You're welcome, Neil. And I would appreciate it if you would listen to me, my friend, and have me discuss these things with you. I have shown you evidence that's virtually, well, you know, like you say, you need to look at it and make your own determination, but I've already made my determination. I think I can support basically every word I said. And this is my theory, which is dipole electron flood theory, and it's dipoleelectronflood.com. There's the nucleus. Now, the only other possibility is it's a layered nucleus like this, with layers, but I don't think so. I think it's this one here. And these are all the negative particles that are surrounded. These are all which have all the energy, the electron neutrinos, and that's where the muon neutrinos are in the center. And they only can separate like this in the subatomic realm. Once you get past this, you have bar magnets. They stay a bar magnets. All of this just explains what's going on. And very, very, very simple. Very, very simple. And it is simple. It doesn't have to be, it doesn't require all this nonsense. All right, so I would certainly like to be able to engage. I tried with Don Lincoln here long, long ago. And he's right down at the bottom. Want a phrase defined? Have a question? Email me. I've done that, and I was told don't ever contact me again. Now, this goes back. It was, boy, it's got to be close to 10 years since I tried contacting Don about this. And so then I decided, well, I'll go to the University of Geneva for particle physics and bring this up with them, which I did. And they were very respectful. They were like, you know, wow, this is amazing, but this is impossible. And I said, no, it's very possible. And they said, no, you can't. There's no way you could take these pictures. You know, it can't happen with CMOS because it would destroy it. And that's when we got into the thing about CMOS. And they ended up, as I think I showed you, development of the high voltage CMOS sensors. And this just happened July 2022. They're making some more new ones for future for radiation tolerance. This is it here. See, CMOS sensors for future hadron colliders, especially in terms of radiation tolerance. All right, so they already did upgrade. They shut down for 3 years. They upgraded the CMOS sensor to use CMOS sensors and something else. I think they focusing magnets they put in too. And that's exactly what I told them. That's exactly what I told them at University of Geneva, who I believe they're hooked in with CERN. I said, you got to focus. You got to get down here where you're focusing through a, I think they were just letting them come by and hoping they're going to hit each other, because they hit them head on. And that's the other problem. They're going to slide off this way and slide off this way. If they're coming into the venturi, they can't get out. They have to hit. We get 100% collision rate. You see that? They can't get out of each other's way. When they have them and they come at each other, they come in like this, and the fields make them go, and they don't smash. Every now and then they get one together, and they get like 25 out of billions. So they have to have 25 hits, something like that. They think that's a big, major accomplishment. Out of billions of particles, billions. And I guess they're doing a little better now since the upgrades to focus and the CMOS. They can see it better. But I think I deserve an audience with the people that have the weight. Like, look at this already. Got almost 3 million hits. All right, Star Talk. So Neil, let's talk. And I'll talk about stars too, because I got some information on those and about the corona of the sun. I want you to tell me what you think the corona is made of and why it's so hot out there. Sun's surface is about 10,000 degrees in that area. Out at the corona, way out here, it's millions of degrees. Why, Neil? All right, I love you all. All I want to do is be seen and have this evidence seen. And it could lead to a lot of things. Because as far as I'm concerned, everything right now is based on the wrong model of everything. I mean, literally everything. And again, we'll do the mud fossils too. I'll do everything. If you're a scientist, you're the guy I'm looking for. Prove it to me, my friend.